I'm Alex Brown, and I'd like to introduce you to the Vibration Analysis Design Tool. This tool takes a typical bay of your steel-framed structural system and analyzes it for vibration performance from human walking. Let's jump in. So getting into the tool itself, first thing you may notice are these tabs across the top here. We're going to spend most of our time in this vibration walking section here. That's going to have all of our inputs and outputs, but there's other tabs here. This one gets into the calculations kind of behind the tool that help power everything, and then a couple just for references for some of the concepts. There's a few print buttons along the side here. They generate a really nice clean PDF for you that you can print off and store in your project files. Everything within the tool is based on the Steel Joist Institute and AISC guidance and codes for vibration analysis. And if you have a project that's more complicated, because this project is only meant for a typical bay within a larger structure for walking vibration. If you need a more complicated analysis or you have a more complicated structure that doesn't have that repetition, FloorVibe is going to be our recommendation. So this is a standalone software that's available for purchase that's going to be able to handle more of those complicated scenarios. So getting into the floor information section here, first thing I want to point to is this vibration occupancy option. So this drop-down is great. It's going to power a lot of the kind of default values throughout the first part of this program. So it starts off on office electronic, but if we were to flip that to office paper, that's going to change some of the beta values, the damping ratios that are happening, and then also the superimposed loading that's being applied to that structure. So a paper office is going to be heavier. It's assumed that there's more dead load. There's more stuff kind of weighing that structure down. So you're going to see higher beta values and higher values here for superimposed loading versus office electronic. You can see some of those kind of changing on the fly there. It's important to note for the superimposed loading that this is going to be quite a bit less than your downward design gravity loading is, because we want to capture what's actually present on the project, not just the worst case scenario that could happen on the project, because these loads actually help resist what that vibration could be. Some spots here to enter the deck and concrete information. And then the bay dimensions, these are really important for the larger floor system is the dimensions of it, because a larger, more repetitive structure is better able to absorb that vibration and internally limit what it could be. So there's a couple of really good tooltips here that sort of explain what's what. There's a reference to the Tech Digest 5, where to go to get a good visual. Or if you just want to sort of mentally picture it, floor width is going to be the length of the girders, and then the floor length is going to be the length of the joists. Moving on, we define what the girders are that sort of frame out a typical bay within this larger area. So these default to joist girders, but you can change those to wide flange and then pick from the drop down what size wide flange you have present. Or if it's just a wall, it's just assumed it's going to be nice and rigid and it's going to resist vibration. We'll leave these as joist girders just for the time being, but there are a couple of options here so you can fine tune what the loading, the span, the depth, if there's deflection criteria, all of that. You can really dial in what that girder is, and the program is making those assumptions in the background on what the resulting moment of inertia is going to be. If you need a larger moment of inertia as like a minimum value, that can be specified as well. So you can see here it defaults to 6,212 just for this particular girder and span. As a result of going through all of these calculations, I know I need a 8,000 inch to the fourth moment of inertia on this member. Perfectly fine. We can supply it that way. We just need to know up front, so that should be supplied on the contract drawings on like a structural framing plan. For now, we'll flip that back to just use default values. Moving on to this joist information section. Again, just trying to define what are those members. So a lot of different categories here. And as you flip through each one, it's going to change what kind of outputs are expected. As you flip through each one, it's going to change what kind of inputs are expected. For a CJ series, it's going to have the three components, the total, composite live, non-composite dead. For an LH series, you can go total over live, or you can flip that to SJI standard and then pick from all of the various SJI member sizes that are available. And then if I flip this to K-series for a second, that default value, the 28K 540 over 400 is a good example where this warning note pops up, a 5-inch seat depth may be required. And that's because of the heavy loading on that joist. It's going to up the top chord angle size that's being used, and a deeper seat's required just to make sure there's no eccentricity in that bearing. So it's really making sure all attributes of the different members kind of are synced up to make sure we're getting an accurate analysis. So in this case, we could change those seat depths to make sure that it's matching that recommendation. And then finally, scrolling all the way down to the bottom here, this is where our outputs are. So this is the result of all of that input and checking the natural frequency and getting the resulting acceleration of the floor. So in this case, 0.58 is higher than 0.55, so it's no good. If I flip this back to a LH series, so back to that default view that you get when you open the tool, we fall right into this range of engineer judgment is required. It may or may not be acceptable. So if this is something that you're looking to improve, my first recommendation is going to be looking at the end connection. Rather than a typical seat, I would recommend a bolted flush frame connection. It's going to perform quite a bit better for vibration and really make Joist a much more attractive option for your floors. So you can see the difference here between the left girder and the right girder. 0.396% is well below the 0.5%. So this is definitely an acceptable check. And if we just flip both sides to that, floor bay is acceptable based on that change. And if I navigate to a different part of our website for just a second, so up top, products, joists and joist girders, and then engineered solutions. And I'll just open that up real quick here. We've got some additional information on flush frame connections and some pictures here. We can do a full depth flush frame connection shown here. It's just a shear tab kind of connection framing into the side of that beam girder. Or we could do a top chord only flush frame. Now, both are acceptable and we'll definitely see that improved vibration performance. And that's the vibration analysis design tool. It's a great resource for analyzing your floor system for basic occupancy vibration. With this tool, you can hone in the design decisions and techniques like using flush frame connections or additional damping to improve vibration performance. And with that, happy specifying.